Okay, for Chapter P, we're going to finish up with talking about how to solve absolute value inequalities and also quadratic inequalities. Okay, we've talked about how to solve quadratic equations quite a bit over the last few days. Okay, but now we're going to switch gears to inequalities. And we're going to find that a lot of the techniques that we've learned so far are going to be pretty similar to what we have already been doing for today. There is an algebraic rule for dealing with an absolute value inequality. Okay? And that rule is if we have anything in absolute values that's less than some constant a, okay, that we can rewrite a new sentence, okay, that's the opposite of a, less than what's in between the absolute values, less than a. Okay, so this is an algebraic approach we can take for finding the solution to that. Okay, and one thing to consider is that when we get done with this, our answer is going to be some interval, okay, between a and negative a. Okay, and we're going to be able to figure out what the values are, okay, that are going to be the solution set to this particular inequality. Okay, the same thing here with greater than sign. Okay, we're going to get two sentences. One's going to be whatever's in between the absolute values less than the opposite of a. Okay, or, and notice I double underline the or here. That's the key word that has to go between these two sentences. And the other sentence is going to be u, which is the stuff in the absolute value, greater than a, which is the constant that was on the right originally. And of course, we can use the or equal to's also, and we'll get the same result. Now, what I want to try to illustrate today, though, is that we really could memorize this system if we wanted to, okay, and make sure that we can do this using algebra every time, okay, or we can try to understand the bigger picture in all this, okay. What we're really asking for here, and I'm going to start with a simple example. If I had something like, if I just had an x in here, if it was the absolute value of x, okay, is less than some constant. Okay, let's review what does the absolute value of x look like. If I do math, num, first one's absolute value of x, and I graph that, okay, the general shape of the absolute value function is the v shape, okay, that we learned in Algebra 2. Okay, now if I had that function and I want to know when it was less than a certain number, like say if it was less than 5, if I were to graph both of those on the same coordinate plane, okay, my question is, when is this curve less than this curve? Well, the left curve is a v, and the right curve is a horizontal line. So wouldn't it be less than that from this point to this point? So the key issue would be, can I find those 2 points? True? Okay, if I can find those 2 points, then I know the answer to this is anywhere between this and this. Okay, and when I say between, notice what we get for the algebra approach. Okay, this represents between two numbers, doesn't it? Okay, and if I were to ask the other question, when is it greater than? Okay, it's greater than the line, okay, up to this point, and then from that point and beyond. True? So when we get done, our answer should look something like this. Okay, we're going to have negative infinity to some value, and then we're going to have or some other value to infinity. Fair enough? Okay. So, now, let's go ahead and put that into practice by starting with an example that I have here. We have x plus 3 in the absolute values is less than 5. Okay. Now, if I take the algebra approach, okay, that I illustrated on the previous page, okay, we would write the following sentence. We'd write down negative 5 less than x plus 3 less than 5. Okay, because remember in this case our a is 5, and they told us in general we're going to put the opposite of a, less than u. U is the stuff that was in the absolute values, is less than a. So we're going to write one double inequality sentence. Okay, and then and again from the algebra approach we would just subtract 3 from all the parts, and we would wind up with the solution set of negative 8 less than x less than 2. Okay, so we can solve that with algebra, but one of the issues that often comes up is, what if we're on the ACT test and we have that problem and we can't remember how to solve this absolute value inequality? What if we can't remember that this is what you do? Okay, do we have to memorize that in order to find an answer for this question? Okay, no, because think about the bigger picture. All we're asking for is, when is this function less than this function? True? So graphing wise, if I were to take a look at the picture and change this to x plus 3, okay, and graph again, if I'm on the ACT test and I have my graphing calculator, okay, even if I don't remember the algebra, should I be able to come up with those two values right there and say when the curve is beneath the line? Okay, got an intersection command. If you intersect these two, it should be -8 and 2. Exactly what we got with the algebra. Okay, and bottom line is that right there is our answer. Okay, if we were to graph that answer, okay, we'd have -8 to 2, both open circles because it's a less than sign. Okay, if we were to put it in interval notation, okay, this is what the solution would look like, because this shows everything between -8 and 2, not including either. Okay, and the other key point I want to mention is that this sentence that I wrote, okay, if we were to separate these two, if we were just to look at this part, okay, our answer would be -8 is less than x. Okay, and then if we look at this one, x less than 2, and we connected those two with an and. Okay, and always means the intersection of those two. Okay, so what we want is we want things that are greater than -8 and also at the same time less than 2. So any numbers that would make that true, okay, will make the original sentence true. Okay, so let's check that. If I were to pick a number between -8 and 2, like say 1 for instance, if I put a 1 in here, I'm going to get 1 plus 3, that's 4. Is 4's absolute value less than 5? Yeah, for sure. And if I pick something out of there just to make sure I think I'm right, what if I pick 3? If I put a 3 in here, that's going to give me 6. And is 6's absolute value less than 5? No. So, but again, is 3 part of the solution set? No. Okay, if I was at 3, okay, my curve would not be below 5, it would be above 5. Same thing with like -9. -9 in here is going to give me -6. And the absolute value of -6 is 6. Is 6 less than 5? No. Okay, and again, why doesn't the -9 work? Because it's outside. If we look at the picture, where is -9? It's over here. And what do I know over here? Okay, the curve is not below 5, it's what? It's above it. Okay, so that's why -9 is not part of the solution set. So the solution set is only from -8 to 2. Any number in between there, okay, algebraically makes the sentence work, and graphically, okay, the curve is below the line. And that's what we're after here. Graphically is when is this curve below this line. Okay.
How did you check that in your calculator?
So, the absolute value is under your math menu, math, num, first one. Okay. All right, let's look at another one. This time we have a greater than. I have 2x plus 3 greater than or equal to 7. So we're going to do it from the algebra standpoint first. Okay, according to that rule I just looked at on the previous page, okay, I'm going to write down u, which is 2x plus 3, is less than or equal to the opposite of a. Our a is 7, so the opposite of a would be -7. I'm going to connect it with an or. And I'm going to write 2x plus 3, which again is u, is greater than 7, which is our a. So I'm just following the rule just like it's written on the previous page. Okay, and then from there, what I'm going to do is solve those two simultaneously. So if I subtract 3 from both sides in this case, I'd get 2x less than or equal to -10, and if I divide, I'd get x less than -5. If I subtract 3 here, and then I get 2x is greater than or equal to 4, divide by 2, I get x greater than or equal to 2. And notice again, the key word that has to be here in this situation is or. Okay, I'll talk about why in just a minute. But before we do that, let's look at the graph and see if the graph agrees. If I do 2x plus 3, and I do 7, compare those two. Again, I'm looking for where is the line, okay, or excuse me, where is the curve greater than the line? Okay, it means where is the curve above the line? Okay, and ultimately, wouldn't it be, if this is our -5 that we just calculated, it's got to be anywhere to the left of -5. And notice what our solution set is. Isn't this left of -5? Okay. And then at 2, okay, when is the curve greater than? The curve greater than would be anywhere to the right of 2. And again, doesn't that describe values that are right of 2? True? Okay. So every time I do one with a greater than, shouldn't it be something like this, where we have 2 different intervals, one going left, one going right? Okay. Just like over here, if it's a less than sign, I should have underneath, which means it would be between the two values that I find. Okay. So less than is between because that's when the curve is below. Okay, greater than is above because that's when the curve is above. Okay. Now, a couple things I want to also illustrate. If we were to draw a graph of those two solution sets together on the same graph, okay, it would look like this. Okay, x less than -5, x greater than or equal to 2. A Could we also plug in values that are in either one of those two and make sure it's true, that it works? You know, if I plug something in here like 1 again, if I put a 1 in here, I'm going to get 5. Is 5 greater than or equal to 7? No. Okay. And hence it's not in the solution set, is it? Okay. Only numbers here and here, okay, would make that sentence true. And also, in interval notation, because we need to be able to go back and forth between any of these three types, okay, the way we'd write that in interval notation is that this sentence is true whenever we're anywhere between -infinity and -5, okay, and also from 2 to infinity. And you notice the symbol that I used here, the union symbol. Okay, the union symbol and or go together. Okay, if there's any kind of or situation where we have two what we call disjoint solution sets, okay, they need to be connected with a union symbol. So disjoint just means that they are two non-overlapping solution sets. Okay. One of the things I also want to address here for just a second is if we were to use the other word here, if we were to put an and here, okay, that would not work, because what and means is intersection. Okay, and if you look at these two, look at the graph, this is the easiest way to see it. Do these two graphs have an intersection? So if I were to put and in here, then wouldn't you really be telling me that the answer is the empty set? Okay, there is no intersection between these two. Okay, so and in here would make that not true anymore, would it? Okay, or means the union. That means I want both together on the same graph. Okay, so make sure we're very careful with the way we use the words and or. Okay, questions so far on the solutions or the graphs for either of these two?